Welcome to another episode of the U. My name is Robert Whitaker. Today we're going to talk about Docker containers and how they utilize storage. I'm going to take you through 4 simple steps. Step number 1, I'm going to show you how a Docker image can act as a file system for containers. The second step is I'm going to show you how containers utilize storage on the underlying guest OS. The third step is we're going to see how containers can have file isolation from each other. And then the fourth and final step is we are going to inspect the Docker overlay file system. All right, let's get started. So before I go through a step-by-step demo, I want to first cover an important Docker concept. So as you might be aware, Docker can be used to create, delete, and manage your containers. So let's say I create container 1 and container 2. Notice container 1 has app 1 inside of it, and container 2 has app 2 inside of it. And one huge benefit that's driving the adoption of containerization is you can have multiple containers and thus multiple applications safely running on the same guest OS. And when containers are running on the same guest OS, those containers can share and utilize the physical servers underlying hardware. So things like CPU, memory, network I/O, and storage. They can share storage. And here we have our first key point. Containers share the server storage that they reside on. Now, before we go through the lab, one other quick concept to cover. Containers are created from Docker images. So you could almost think of Docker images as like templates. And then we can spawn our containers from those images or those templates. Now, before I create a container, just a quick note. Previously, I kept referencing when we set up our containers, they're going to run on top of a Linux guest OS. But as you see here, I'm at a Windows prompt. So what's going on? So what I did was I installed Docker Desktop on Windows. And the way Docker Desktop works is when you install it, it deploys a hidden Linux virtual machine running on my Windows machine. And the way Docker Desktop works is I'm going to run Docker commands from my Windows command prompt, but those Docker commands are going to get sent to a Linux VM that has Docker installed. So if I create or delete containers, I run commands from the Windows CLI. Those commands get sent to the Linux VM, and the containers would get created and would run on top of that Linux VM. All right, so now that we covered my setup, let's go ahead and create some containers. So I'm going to run the Docker images command. This is going to allow me to see all the images downloaded to my Linux VM. And notice here, I have the Ubuntu 23.04 image downloaded to my OS. And I'm going to create a container from that. All right, so I'm going to run the Docker run command. So the container name that I want to create is going to be container number 1. And I want to create that container from the Ubuntu 23.04 image. And when I create that container, I want to launch the bash process, and there we go. So next what I'll do is I'll run the docker ps command. This will allow me to see the running containers, and I can see right here that container 1 was created, and it was created from the Ubuntu 23.04 image. Next, we're going to attach into container 1. So I'm going to run docker attach container 1. I hit enter, and notice when I do that, my prompt changes from a C prompt to this. This is the actual container's ID. So I'm actually inside of container 1 right now. And if I type the ls command, I can view the files and folders within container 1. So we just created container 1, and it's running on the Linux guest OS. And we saw container 1's file system. But that begs the question, how does container 1 store those files and folders on the underlying guest OS? And that's where Docker images come into play. I said before, Docker images were like templates from which we can spawn our containers from. But there is a lot more to Docker images than just acting as templates to create containers. Docker images play a significant role in container storage architecture. And here we have our next key point. Docker images are read-only files that act as read-only file systems for their respective containers. When I do an ls from container 1, it's reading its file system. So it's seeing its folders and files by looking within the Docker image. What do you think might happen if I go in and try to delete the Ubuntu 23.04 image right now while container 1's running? Let's go take a look. So I'm in the container right now. I'm going to go ahead and hit Control PQ to exit from the container. And then what I'm going to do is I'm going to run the Docker image command, and I'm going to try to remove that Ubuntu 23.04 image, and let's see what happens. Drum roll. Oh, I must have had a typo. Oh yeah, add an extra U there. Let's try it again. Drum roll. Okay, it gives me an error, right? It's saying we're unable to remove Ubuntu 23.04. You have to force it. Container 1 is using it right now. So in order to actually delete that Ubuntu image, I would first have to stop and remove container 1. Then I could delete that image. And when you think about it, this makes sense. We do not want to delete container 1's file system. That would be very, very bad for container 1. So previously, we created just one container from one image. However, you can create more than one container from that same image. And here's one of the really cool things about how Docker containers work. Containers can share the same image as their read-only file system. So if I create container 1 and container 2, both from that Ubuntu image, when I do an ls from container 1 or do an ls within container 2, it's reading its files and folders. It's reading its file system from its Ubuntu image. So let's go in. We're going to create another container. I'm going to run the exact same command that I ran before, but I'm going to create a new container. I'm going to name it container 2. It's going to be based off of the Ubuntu 23.04 image. I hit enter. And let's run the docker ps command to confirm that both of the containers are running on the system. Right? There we go. We can see we have container 1, container 2, and they're both using or created from that same image, and they're both going to be using the Ubuntu 23.04 image as their read-only file system. All right, so we just completed step 1. We created multiple containers from the same image, and then we saw how a Docker image acts as the file system for the respective containers. We're now going to move on to step 2, and we're going to view how the containers and the Docker image they were created from utilize storage space on the underlying guest OS. So the next command that we're going to run is the docker ps, but this time we're going to specify -s, and this is going to allow us to see some storage statistics for our containers. Now, if you look at this output carefully, how much space do you think container 1 and container 2 are utilizing on the underlying guest OS? The answer is 0 bytes. Yep, that's correct. I said 0 bytes. You see, containers created from the same Docker image on the same guest OS, they're sharing the same read-only file system. So in our example, the containers aren't taking up additional storage space. The image, the Ubuntu image that is acting as the read-only file system, that is taking up the storage space. The containers just point to that file system, to that image. In fact, the read-only file system that we're using, the image that we're using, is 70.3 megabytes of storage space. And we can confirm the size of the Ubuntu image that we downloaded using the docker images command. And I can see right here, in fact, our Ubuntu image is 70.3 megabytes. Now this image right here illustrates what we just set up. Both container 1 and container 2 were created from the same Ubuntu image. Thus, they're sharing the same read-only file system. The Ubuntu image is 70.3 megabytes, and container 1 and container 2 are just pointing to that read-only file system, so they're technically taking up 0 bytes. Now, what do you think might happen if we create some additional containers from this same Ubuntu image? How do you think it's going to impact storage utilization on the underlying guest OS? All right, so let's take a look at this. I'm going to go back and I'm going to create container number 3 from that same Ubuntu image. And I'm going to create container number 4 from the same image as well. And let's go ahead and rerun that docker ps-s command and take a look at the output here. I have 4 containers. They are all based off of the same image. They are sharing the same file system. They are taking up 0 bytes of data. The file system or the image they're pointing to is 70.3 megabytes in size. So notice we just created container 3 and container 4. And guess what? I create more containers from the same image. The total space utilized on the underlying guest OS stays the same, because those 4 containers are pointing to the same file system. This is kind of one of my favorite concepts of containers. To me, this is like major data deduplication here. We have 4 different containers, 4 different applications pointing to the same file system. Pretty cool stuff. All right, let's go ahead and go back into the lab. I just want to quickly remove container 3 and container 4. To do that, we first have to stop those 2 containers. And then I'm going to go ahead and remove both the containers. And then next, I'll just type the docker ps command to confirm that container 3 and 4 are gone, yet we still have container 1 and 2 still running on the system. So we just completed step 2. We were able to view how containers and their Docker images utilize storage space on the underlying guest OS. We're now going to move on to step 3, and we're going to try to create a file in one container and then see how that container utilizes storage. So let's go into container 1. So I'm going to type the docker attach command, and I'll specify container number 1. Notice the prompt changes, so I'm in the container. And what I'm now going to do is I'm going to use the truncate command, -s. I'm going to create a 10 megabyte file, and I'm going to name that file hello _ Uncle Bob. I hit enter. Okay, we created the file. Let's go ahead and type the ls command, and I should see the file within container 1. Now let's detach from container 1 by hitting Control PQ, and I'm back to the main prompt. Now that we created the hello Uncle Bob file in container 1, let's go into container 2 and see if we can see that file in container 2's file system. So I attach into container 2, its prompt changes. I type the ls command. Notice there's no hello Uncle Bob file. So this image right here depicts our current setup. Container 1 and container 2 are still sharing the same read-only file system, the Ubuntu image, but we attached into container 1. We created the hello Uncle Bob file. We can see that file within container 1. However, when we attach into container 2, we don't see that file. So this begs the question, if container 1 and container 2 both share the same read-only file system, how can they have their own unique files and folders within their respective container? And that's where something called the read-write layer comes into play. So although containers can share the same read-only file system, each container is gonna have its own unique read-write layer. So let's talk a little bit more about the container's read-write layer. In this visualization, Container 1 is still able to read its file system from the Ubuntu image. However, when I created that new file within Container 1, that new Hello Uncle Bob file gets written and stored somewhere else. It gets stored in a dedicated read-write layer for Container 1 only. Each container's read-write layer is stored in a unique directory on the underlying Linux guest OS. Now, if we look at Container 2, it's still going to read its file system from the same image that Container 1 does. It's still going to use that Ubuntu image. However, if we look at Container 2's dedicated read-write layer, it's empty. There's no Hello Uncle Bob file in it. There's no data in it. And when I attach into Container 2, we didn't see the Hello Uncle Bob file. Now let's go back to our example. I'm going to go ahead and detach from Container 2 by typing Control-PQ. Let's clear the screen. Now let's go ahead and rerun the command, the docker ps -s command, and let's see how our containers are utilizing storage. Now notice this output looks different. We can see Container 1, its read-write layer is taking up 10.5 megabytes of storage space on the underlying guest OS. That's because we just created that 10 megabyte Hello Uncle Bob file in Container 1's read-write layer. Now you might be thinking, okay, where does this number come from? 80.7. This is the number of the container's read-write layer, which is 10.5, plus the size of the Ubuntu image, which is 70.3. That equals around 80.7, or 80.8 technically, but they're displaying 80.7, and I'm guessing we're seeing a little inconsistency in the numbers, maybe due to some kind of rounding down and conversions and that kind of stuff. Now, the important thing is to kind of understand the big picture concepts. So in our setup, Container 1 is utilizing 10.5 megabytes of space in its read-write layer. Its base image is utilizing 70.3 megabytes. If we add those two numbers up together, that equals around 80.7, 80.8, and that's what we were seeing in that previous output. All right, in step 3, we created a 10 megabyte file in one container, and then we saw how that container utilized storage. It wrote it to its read-write layer. In step 4, we're going to talk about and inspect the overlay file system that Docker uses to make all this happen. So we're going to answer the question, how do a container's read-write layer and read-only file system work in tandem? Docker uses what's referred to as an overlay file system. So you can almost think of the container's read-write layer as like the overlay, and you can think of the container's image as the underlay. So what happens is Docker will merge the contents of the read-write layer and almost like place it on top of the image. And what that does is it forms into a single unified view of the container's file system. So when we were in the lab and I attached into Container 1 and I run an ls command, I saw Container 1's file system. But really Container 1's file system took the contents from Container 1's read-write layer, coupled with its read-only image, read-only file system, and it formed a unified view of the file system. Remember, the Hello Uncle Bob file is in Container 1's read-write layer, and the rest of these folders and files are in the container's read-only file system in that Ubuntu image. So let's go back into the lab, clear the screen, and I'm going to run the docker info command. So I got a lot of output, but if we look right here, there is the storage driver. Docker uses overlay 2. It overlays the read-write container layer on top of its read-only file system. All right, the next command we're going to run is the docker inspect command. Docker inspect container 1, we're going to run this command and to get a better idea of how this overlay file system works. So I hit enter. We're going to get a lot of output. I'm going to browse right back up here. And notice there's a data key. And within the data key, we have all these paths, these directories. These are referencing paths on our Linux VM where Docker is installed. Now, if we look at the different paths, they have different keys. And we have what's referred to as the lower dir, we have the merge dir, and we have the upper dir. The upper dir contains the path to container 1's read-write layer. This is unique for container 1. This is where the Uncle Bob file is stored in the upper directory. The lower dir directory, that represents the path to container 1's read-only file system. That's that Ubuntu image. And then finally, the merge dir directory, that reflects the path to container 1's unified view of its file system. So let's clear the screen. And if I attach into container 1 and I type ls, we're viewing the contents of that merged dir directory. The hello Uncle Bob file is in that upper directory, the container's read-write layer. The rest of these folders and files within those folders are going to be in the lower directory. And that forms the merge directory. That's what we're looking at right now within container 1. Well, guess what? Container 2 is going to have a different merged directory because its upper directory is different than container 1's. And finally, let's go ahead and just clean up our work. So I'm going to go ahead and do docker stop container 1 and container 2. Oh, I messed that up. My fault. And now we're going to remove the containers. And now I'm going to go all the way back to a command we were running, if I can get there. Oh, yeah, there we go. Remember we ran this command earlier. It failed. It failed because container 1 and container 2 were using that as its read-only image. Well, now that we deleted container 1 and container 2, what do you think might happen? Do you think we're going to be able to delete that file system? Let's see. So we got our drum roll. Enter. Boom. There we go. We can now delete the Ubuntu image because no containers are actively using it at its file system. All right, that's all I got for today, guys. I hope this was useful, and I appreciate you taking the time to watch this video. Thank you so much.